Deal? All right. Okay, so it says, why do we care about finding Taylor series for particular functions, such as the problems that we did in yesterday's lesson, or Friday's, and the problems that you did for homework? For instance, why is it so important to know that we can write sine of x as x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on?
Wait, I'm sorry, my notes got all messed up this time. I've got to fix these really quick.
Well, this is all just written out, so
I
you're
said,
not
can we do our
mismatching.
lesson on the floor today?
No.
I
Trig
would
functions
prefer not.
lack finite algebraic formulas. Power series are the next best thing. So using power series
No, it's your Steve, the two.
allows us to find approximate but very accurate values of trig functions as well as other transcendental functions. All right.
Are
Says-
transcendental functions just like infinite?
Transcendental.
Because like sine goes on forever, right?
Yeah, but most functions, or a lot of them I should say, do. Let's see.
Or yeah, all functions do go on forever. What does it mean?
Ugh. Function not expressible as a finite combination of the algebraic operations of addition, subtraction, multiplication, division, raising to a power, and extracting a root.
So it's like
So.
not having a formula for it?
Right. Yep. Not a finite one anyway. Okay, so use the Maclaurin series for sine to approximate sine of 1 so that the error in your approximation is less than 1 over 1,000 without using a calculator. So sine of 1 would be, we're just plugging in a 1 instead of an x into our Maclaurin. So instead of x, I now have 1 minus 1 cubed over 3 factorial plus 1 to the fifth over 5 factorial and so on. But I need to know how far I have to go because I need an error of less than 1 over 1,000. Well, what type of series is this?
Alternating.
It is alternating. So since it's alternating, I know I have my alternating error is always what?
Like the sum thing?
The next term.
Yeah, it's
Yeah.
smaller than the next term, right? So I can stop when the next term is something that's smaller than 1 over 1,000. So
Do we know why that is, or is it just
It was
something
just
you
like
need to memorize?
something we learned.
well, I always like to think about it like this, or like your rainbow.
Oh yeah.
Remember when we did this?
Yep.
We're getting closer and closer to that sum.
Mhm.
So this is my number line, and I start over here, and then I bounce over here, and I'm getting closer and closer and closer and closer and closer. The difference between this and the actual sum
Mm-hmm.
can't be this far, right? Because this is in between what I added up and that next term. So the distance from here to the actual sum is going to be smaller than the distance from here to that term. Because we're just bouncing closer and closer around.
Yes, that makes sense. Okay.
Or sometimes I think about it like this, like we're leveling off to something. Let's say this is the value of the sum, and I'm bouncing around it, but really it's more, this is a more accurate view.
I like the bottom one
If-
better because you can visualize the distance.
Is it possible to do that if it's conditionally convergent?
Well, just anytime it's an alternating series, this will work,
Okay.
conditional or not. Yeah. Okay, so 7 times, all right, this is 1, when that happens. This is 1 minus 1 over 6 plus 1 over 120 minus 1 over, this comes to 5,040. And we can keep doing that, right? But I don't need that many because
This one.
absolute value of that is smaller than 1 over 1,000, right?
Right.
So I can stop here. Because it's got, the error is going to be smaller than the first truncated term. So if I truncate, then this is going to be smaller than the actual error. And it's smaller than the error that we need. So I can just add up the first three terms. Oops. And this is an approximation. 101 over 120, which is approximately 0.84166. We would obviously have to have a calculator for that part. All right. So already kind of talked about this, but since the terms alternate, decrease in magnitude, and what's the other thing?
Another
Limit
equals zero.
That's right. And have a limit of 0. Then the error I don't know what that's supposed to do, but anyway, the error is less than the first truncated term, which is less than 1 over 1,000, by alternating series error bound or remainder bound, either way. Alright.
So whenever we have like these type of like series, and are they always usually alternating?
Are McLaurin ones?
Like just the sine and not cosine. Yeah, the sine and cosine ones are always alternating.
Yes. Sine and
So-
cosine are.
But what about like if we don't have alternating ones? Can we still do this?
If you don't have alternating ones, then you can't use alternating series error bound, so you can't say this about the actual sum.
Are there
Um,
other ways?
I don't
We
think they'll
haven't
ask
talked
you.
about it. Okay.
The only other one would be the Lagrange error bound, and we'll do that after spring break. I'm not gonna throw that at you right now. But
Okay.
yeah, you'll only see this if you can use it for alternating series. So if we want to know the actual error, then I'm gonna plug this into my calculator, get the actual value, and find the difference between that and what we estimated, right? Which was 0.84166. So error. So even after only 3 terms, that's a pretty good estimate, right? Probably helps that it's pretty close to the center at 0. Or the further we get away from that, the less accurate it's going to be.
They did.
Oh.
Or they're close to did, I guess.
Does it tell you when it's close to that?
Huh?
Does it tell you when it's close to that?
Yeah. That's
Okay. Alright, find in series form an antiderivative for sine of x squared and then use it to approximate the integral from 0 to 1 of sine x squared. So the error in your approximation is less than 1 over 1,000 without using your calculator. Okay. Well, first I'm just going to figure out what this Taylor series is going to look like. So I'm plugging in an x squared everywhere I see an x right into that polynomial. So I started out with x. When I plug in an x squared there, it just becomes x squared. Then I had an x cubed. When I plug in an x squared, that becomes x to the 6th. The bottom stays the same. X to the 10th. I'm really just multiplying all these exponents by 2, right? Because when I have an exponent, 2 and exponent, I multiply. So 5 factorial minus x to the 14th. Oops, 7 factorial. And so on and so forth. Okay, and so I can integrate this because I can integrate each piece of it. right? So find the antiderivative for sine of x squared. That's the first thing they want us to do. Oh, they didn't do that part, but we're going to, I guess. Okay, so in series form, this would be x cubed over 3 minus x to the 7th over 7 times 3 factorial, x to the 11th over 11 times 5 factorial, x.
Where are you getting the numbers on the bottom?
I'm using this
Mm-hmm.
and I'm integrating each one.
Oh, you're into okay. Right.
And I would put, if I don't have bounds here, which if they want the antiderivative and they don't give me bounds for the first piece, I'm just gonna put a C there because there could be a constant, right? Can't forget our plus C. And just to keep going, let's try to write a general term for this. I always think it's easier to start with what we know. For sine x, what was my general term? So that x cubed. We had a negative 1, right?
1 to the n
And then my x was raised to the
was odd. So
2n plus 1 because it's odd. And then we
the same on
divide.
the bottom.
Yep, because it will match that exponent, right? Okay, this is what we started with. So when I plug in an x squared, what happens to my general term? Oh, what in the Sam Hill? That was way too many squiggles. So this is the sum from n equals 0. Would that work? 0? No. 1?
Mhm.
Well, that would make that negative though. But otherwise, oh yeah. I'm looking at this, but this is the original, so yeah, 0. Okay, so it'd be this. Then, the only thing that's different is I'm doing x squared to the 2n plus 1. I'm plugging in an x squared, right? Everything else stays the same.
Here's my Kirby slip.
I could, thanks.
Oh.
I could simplify this and distribute that 2. So that's x to the 4n plus 2. Okay, now I'm doing this because if I want a general term for this, I'm integrating these, okay, or this one in particular, or this one, doesn't matter. I'm going to use this one because it's a little bit easier. So my general term is going to look like, and now I'm just going to think about, okay, this doesn't change. I'm still alternating negative and positive, right? So I'm going to leave the negative 1 to the n alone. But when I integrate, I add 1 to my exponent. Okay, we've done that for a long time. So adding 1 to that exponent is going to be at 4n plus 3 instead of plus 2. And then I divide by that new number. So I'm dividing by whatever that exponent is. And I still have my factorial here.
So,
what you go ahead.
would you be able to just, could you leave it unsimplified, or do you need it in that form for
No, you could, I mean, you could do it to this one.
Okay.
So what you did was you plugged in the x squared into the x spot and then integrated.
Yes. Yes. This is going from the original to plugging in x squared, and then this is going from x squared to the antiderivative. Okay. Now, they want us to approximate the integral from 0 to 1 of sine x squared. I'm going to use a different color just so it doesn't get so messy. Integral from 0 to 1.
Oh, that's nice. Wait, did we steal it or she just keeps letting us use it? No, she was just extra nice.
That's so
Oh.
kind.
Did
In the world.
we steal it?
I don't know.
Did we get this honestly, or?
Just feels too good to be true.
Oh, I thought this was a baby. It's half.
Yeah.
Okay. So this is just gonna look just like that, except I don't need my plus c anymore because I have bounds now. So x cubed over 3, x to the 7th over 7 times 3 factorial.
I have that out of space. Next question, roll. Oh, is it?
Yep.
Oh, I'm so dumb.
No.
Mikey. His
Wait,
words.
what did you say?
Like Mikey.
Yeah.
His words, not mine.
Okay. From 0 to 1. So when I plug in 1 first and then subtract, when I have zeros, all that's going to just be 0 anyway, right? Because I have x's everywhere. So it's going to be 0 minus 0 plus 0 minus 0 plus 0. So the only thing I'm really worried about is plugging in a 1. So that's going to look like,
And it's all gonna have 1 in the numerator.
that's right.
Great.
Yeah.
Wow.
So then to factorial.
What?
Okay. Now we are only estimating this until we get an error of less than 1 over 1,000. Well, notice that the integral is also an alternating series, right? Positive, negative, positive, negative, positive. So it's going to follow those same rules. They're decreasing in magnitude because the bottom's growing, the top is not. It's just a bunch of ones. And so that limit is approaching 0. So that means we can use the alternating series error bound, which means I can truncate this as soon as I get to the term that's smaller than 1 over 1,000. I can stop right before I get there. So this is 1/3 minus 1 over, let's see, 3 times 2, so 6 times 7, 42, plus, I'm not doing that one in my head. 11 times 120. We don't need to know that exactly because if I'm trying to find one that's less than 1 over 1,000, 100 times 10 would be 1,000, right? And these are both bigger than 110, so this is going to be bigger than 1,000. So that's bigger than 1 over 11 times 120. That means I can stop right here.
Woohoo!
So my approximation is going to be just 1/3 minus 142 which also reduces to 13 over 42 or 0.3095 if we use a calculator. All of these would be sufficient. Okay, now we're going to justify it just like we did the last one. So error is less than 1 over 11 times 120, which is less than 1 over 1,000. And this is by the alternating series error bound. Yes, or remainder bound, either one, same thing. Use your calculator to find the actual error. So again, we'll plug in the integral from 0 to 1 of sine x squared into our calculator, see what that gives us, and then we'll subtract that from our error. Or subtract the error from that, either way. So, when you plug it into your calculator, this gives you 0.3102683.
Wait, the top part was all part of part A, right?
Yes.
Try to can do the computer things. Bueno. See when we trash.
Still pretty accurate, right?
Wait.
And that was only with 2 terms, whereas before we needed 3 with the original sine of 1. All right, write a Maclaurin for f of x equals e to the x. This is another one of those that I want you to have memorized. I think
Am I crazy
we've done
or-
this before, right?
Yeah, this is
Yeah.
on the
We
homework.
talked about
Yeah, because, yeah.
e to the x.
Yes.
Practice though.
Yeah, so you can just fill that in, I guess. E to the x is nice. It follows a nice, neat pattern.
It's
X
just
to
plus.
the n over n factorial. Yep, and it's positive all the time. All right. Use your answer to find. Oh boy. Okay. Let's do the limit as x approaches 0 of Okay, so f of x is e to the x. We're trying to find the limit as x approaches 0 of f of x minus 1. So I'm going to substitute, since these are the same, these are equivalent, I'm going to substitute this. You can even do this in 2 steps if you just want to see it, but I'll go ahead and write that out just so you can see it. But I could substitute f of x with e to the x, right? And I can substitute e to the x with this series. So instead of e to the x, I'm going to write it as 1 plus x squared over 2 factorial. It's funky. Plus x cubed over 3 factorial. X to the 4th. And that's going to keep going, right?
Is that all still over 2x?
Yes.
Okay.
Yep, so I'm just substituting e to the x right now. I still have this minus 1, and I'm still divided by 2x. So check this out.
Check this out.
Check it out. I just love
Whoa.
canceling. I love writing something that looks so scary, and then it's like, oh, it's only this. So 1 minus 1, that will go
0.
away, right? 0, that's right. Thank you for your enthusiasm, Abigail. I appreciate it.
Oh my
Is
goodness.
that indeterminate form?
No, because that x is going to go away on the bottom.
Well,
Because it's going to cancel.
Yeah, because it.
yes, it would be.
0.
Look.
Yes, it would be, because if I plug in 0, it would be 0 all the way up here, 0 on the bottom. So we could do L'Hopital's, but also I can actually just divide by 2x, right? I can just divide all of those. So x over 2x just becomes what?
1/2.
1/2. X squared over 2 factorial over 2x becomes what?
X over, no, wait, just x. No, x over 4.
Yeah, x over, well, yeah, it'd be x over 4. I'm going to write it as 2 times 2 factorial, even though it is just 4, just so I can write out the pattern too.
Yeah.
But either way, then the x's are going to take 1 away from that exponent, and then these are both going to be in the bottom, so 2 times 3 factorial plus x cubed over 2 times 4 factorial, and that pattern is going to continue.
Wow.
Now, 1/2 plus x over 2. As x approaches 0, what does this limit become?
1/2.
1/2. But you are right. So this is indeterminate form. So let's check with L'Hopital's. Alright, so we started out with the limit as x approaches 0 of f of x minus 1 over 2x, which is the same thing
No space, guess not.
as e to the x minus 1. Did you try flipping it over?
Yeah.
Yeah.
It's so hard.
Alright, when I plug in 0 here, e to the 0 is 1, so I get 1 minus 1 is 0 over 0. So I'm going to use L'Hopital's. What's the derivative of e to the x? Okay, and what's the derivative of 2x?
2.
Right, so negative 1, that's 0. So I end up with e to the x over 2. And now when I plug in 0,
1 over 2.
that's right.
Why would you look at us to begin with?
Look at that. Okay, cool.
Because sometimes you can't,
But
This
sometimes it's
time.
easier.
but
We
Well, that's
in
simple
this
that was.
case we can. Alright, that's it for today.
Alright.
That's